All right, let's talk about one of the biggest hurdles in Calculus 2, really complex integration. The kind that just makes you stare at the page. Well, I'm here to tell you that the secret to getting good at it isn't about memorizing a million different formulas. No, it's about learning to see the patterns and picking the right strategy for the job. So take a look at this. I mean, seriously, look at that thing. If your first thought is, I have no idea where to even start, you're definitely not alone. It looks like a total mess, right? A jumble of trig functions and powers that feels like a brick wall. But here's the thing. What if I told you there's a system for this? A way to look at that problem and know almost instantly exactly which path to take. It's not magic, and it's not about memorization. It's about training your brain to spot specific patterns. Think of this as your field guide for turning that confusion into a confident, clear, step-by-step plan. We're going to approach this like a gauntlet, a series of challenges. But here's the trick. Each challenge has a tell, a clear sign that gives away exactly how to solve it. Our job is to build that mental toolkit so you can recognize the signs and conquer these problems. So our one and only goal here is to build a decision-making framework. By the time we're done, you'll be able to look at two huge categories of tough integrals, immediately spot the pattern, and then pull the right tool out of your kit to solve it, systematically. No more guesswork. Let's start with our first major category. This is the one you see all the time. Integrals that are just a big mess of trig functions raised to a bunch of different powers. This is where pattern recognition becomes your superpower. We'll kick things off with the classic duo sine and cosine. Whenever you see an integral with sine to some power and cosine to some power, everything, and I mean everything, comes down to those exponents m and n. They are the clues that tell you exactly what to do. And this right here, this is your game plan. It's that simple. If the power on cosine is odd, your strategy is to save one of those cosines for your du and set u equal to sine. If the power on sine is odd, you just do the mirror opposite. And if you get that tricky case where they're both even, well, that's your signal to switch tactics completely and bring in the half-angle formulas to break things down. Let's see this in action, because this is where it clicks. The power of cosine here is 5. That's odd. So what does our blueprint say? Peel off one cos of x and set it aside. That's going to be our du. Now for the magic step. You use the good old Pythagorean identity to turn the leftover cos 4x into sines. The moment you substitute u equals sine of x, that whole terrifying thing just collapses into a simple polynomial, something you've known how to solve for ages. That's the power of this strategy. Okay, let's move on to the next common pairing, tangent and secant. The same big idea applies. The exponents are still the key, but the rules are just a little different, simply because their derivatives and identities are different. So here's the new blueprint. If the power of secant is even, you're going to save a secant squared factor. Why? Because that's the derivative of tangent. If the power of tangent is odd, you save a secant x tan x factor because, you guessed it, that's the derivative of secant. And if you run into that last tricky case, tangent is even but secant is odd, that's your flashing red light that u sub isn't the way. That's when you know to reach for a different tool, like integration by parts. And would you look at that? The problem from the very beginning fits perfectly into our second case here. The power of tangent is 3, it's odd, so we just follow the steps. Save 1 secant x tan x, that's our du, convert the leftover tan squared x into secants, and just like before, the second we substitute u equals secant x, the whole problem transforms into a simple polynomial. The monster from the first slide was just a puzzle, and now we know the solution. Okay, awesome. But what happens when the integral doesn't have a bunch of trig powers? What if instead it has one of these nasty-looking square roots? Well, this is our second major pattern, and it calls for a totally different but very powerful technique, trigonometric substitution. The trigger for this is 100% visual. If you look at an integral and you see one of these three specific square root forms, that's your cue. Your brain should immediately light up and say, aha, this is a job for trig sub. And this table is the heart of the whole technique. Each of these radical forms is basically a Pythagorean identity in disguise. By making the right substitution for x, you can transform the stuff inside the square root into a single, perfect square. It's a brilliant, shape-shifting move that completely unlocks the integral. But, and this is so important, there is a final step that's so easy to forget, After you've done all the work and solved the integral in terms of theta, you're not done. You started with x, you have to end with x. To do that, you draw a simple reference triangle based on your original substitution. That triangle becomes your dictionary, letting you translate your answer from the language of theta back to the language of x. So we've just broken down two massive, intimidating categories of integrals. Let's pull it all together into one master strategy, a final blueprint you can use every single time you see one of these problems. And here it is, your 5-step mental checklist. First, identify the big pattern. Are we looking at trig powers or a radical form? Step 2, check for the specific clues. Are the exponents odd or even? Which radical shape is it? 3, choose your tool based on those clues. 4, execute the plan and solve the simpler problem. And finally, the all-important step 5. If you made a substitution, you have to convert back. And remember, these are not just abstract puzzles to solve for a test. These techniques, this is the math that allows us to calculate the arc of a bridge, to model how populations grow, to process signals in electrical engineering. You now have the blueprint. So the real question is, what real-world puzzles are you going to solve with it?